Right now, as you're watching this video, a comet is racing toward Earth at incredible speed. And what happened to it in mid-September has astronomers around the world scrambling to their telescopes. Comet C 2023-A3, Tesuchinshan Atilas, known as SWAN, didn't just brighten unexpectedly. It exploded into near-naked-eye visibility in what scientists are calling one of the most dramatic comet outbursts in recent memory. The amateur astronomers in Japan and Australia were the first to spot the change, capturing images that showed a sudden surge in glow and the beginnings of a wider tail. Within hours, online astronomy forums were buzzing. Reports poured in from across the globe, confirming that SWAN was no longer a faint, distant smudge, but a living, evolving spectacle visible even without heavy equipment. This kind of outburst points directly to activity inside the comet itself. Beneath its icy surface, volatile materials like carbon dioxide and methane, frozen solid for millennia, suddenly found a way out. As the sun's heat penetrated deeper, those trapped gases vented explosively, blasting dust and ice into space. The result was a massive expansion of the coma, the glowing envelope surrounding the nucleus, and a dramatic growth in the tail. Scientists note that these events are more than just fireworks in the sky. Each outburst is a clue, revealing the hidden structure of the comet's core. Did a new vent open? Did part of the crust collapse? Or did heat trigger buried reservoirs of volatile ice? No one can say for certain, but what is clear is that SWAN has entered a new, unpredictable phase of activity. From this point forward, every night of observation mattered, because the comet's behavior had veered off the expected track. For skywatchers, this was a turning point. Comet SWAN was no longer just a faint object tracked in silence by observatories. It became a global spectacle, an unfolding mystery in the night sky, bright enough to excite the public and complex enough to puzzle scientists. Not long after its sudden outburst, Comet SWAN revealed its true scale. Its tail, once modest and faint, ballooned to an astonishing size, stretching more than 2.5 degrees across the sky. To put that in perspective, that's wider than 5 full moons lined up side by side. For anyone looking up with binoculars or even a small telescope, this wasn't just a blurry smudge. It was a structure that demanded attention. The tail itself told a dynamic story. The brighter dust tail spread outward in a broad, golden fan. This dust was heavier, moving slowly and lingering close to the comet's orbital path, reflecting sunlight in soft, shimmering arcs. But right beside it, a second feature appeared: the delicate ion tail. Electric blue in color, this tail was formed by charged particles, stripped away from the comet by solar radiation and pushed back by the solar wind. Unlike the dust tail, the ion tail was fragile and alive, rippling and bending, sometimes snapping into sudden new shapes. Observers quickly noticed intricate details: knots of dust, kinks in the ion stream, faint rays extending like glowing threads across the stars. Each night the view shifted. What was visible yesterday might vanish the next, replaced by fresh plumes erupting from the nucleus and carried outward into space. Even amateur sky watchers could catch the changes with nothing more than a camera on a tripod, stacking exposures to reveal the comet's evolving form. For scientists, this was more than a spectacle. The sheer scale of the tail meant that SWAN's interaction with the solar wind was on full display. The comet became a natural laboratory, where the forces of dust, gas, and charged particles could be seen reacting in real time. Every ripple and every twist in its structure carried information about solar activity, cometary chemistry, and the fragile balance that governs a comet's life. For the public, though, the message was simpler: look up. A celestial visitor was painting a streak across the sky wider than any city skyline, a sign that even in our modern technological age, the cosmos can still surprise us with raw, unfiltered beauty. As Comet SWAN's display grew, it wasn't just professional observatories turning their instruments toward the sky. Across the world, amateur astronomers stepped into the spotlight. From backyards in Australia, hilltops in South Africa, and rural fields in Argentina, enthusiasts armed with binoculars, small telescopes, and digital cameras began documenting SWAN night after night. Their efforts produced far more than pretty pictures. These observers collected light curves, carefully tracking the comet's brightness changes and confirming the unusual surge that had startled professionals. They recorded tail structures through stacked exposures, revealing subtle bends, ripples, and sudden breaks invisible to the naked eye. Some even compiled time-lapse sequences, capturing in a few hours the kind of dynamic changes scientists usually only see in models. International astronomy forums lit up with activity. Dozens of images were shared in real time, compared and analyzed, creating a collaborative global experiment. A comet visible across so many regions meant that as night ended in one hemisphere, another group could pick up the watch and continue the record, giving researchers near-continuous coverage. This is where citizen science truly shines. The collective power of thousands of amateur astronomers provided a stream of data professional telescopes alone could never achieve. Every color shift, every kink in the ion tail, and every spike in brightness was logged, reported, and stitched into a global record. Even small details, like whether SWAN's coma appeared slightly more golden one night or more bluish the next, added valuable pieces to the puzzle of what was happening deep inside the comet. For the public, it was an invitation to participate. Anyone with a modest pair of binoculars or even a smartphone camera under dark skies could join the effort. For science, it was proof that big discoveries don't just come from billion-dollar observatories. Sometimes they come from someone in their backyard, pointing a lens upward and capturing history as it happens. Just as Comet SWAN was entering this dramatic new phase, the Sun decided to make its own move. On September 28, 2025, solar monitors registered the strongest flare in months, an M6.4 class eruption. For days, the Sun had been relatively quiet, with little activity to report. Then, without warning, one of its active regions unleashed a massive burst of energy. Within minutes, X-ray detectors aboard satellites spiked. Space weather centers scrambled to assess the event. Soon after, coronagraph images confirmed what astronomers suspected. The flare was accompanied by a powerful coronal mass ejection, or CME. This colossal bubble of charged particles blasted outward at nearly 900 kilometers per second, fast enough to cross the distance between the Earth and Sun in less than 2 days. Fortunately for Earth, the CME wasn't aimed directly at us. Our planet was safe from potential geomagnetic storms and satellite disruptions. But the real intrigue lay elsewhere. Trajectory models showed the CME sweeping into the same sector of space occupied by Comet SWAN. For the first time in years, a comet with a vast, delicate tail was directly in the potential path of a solar storm. This raised the stakes dramatically. Scientists knew that SWAN's ion tail, made of electrically charged gas, was especially vulnerable to solar wind interactions. A CME slamming into it could trigger sudden, visible changes, brightening, tail disconnections, or entire segments snapping away and drifting into space. It was as if two cosmic forces, one from the frozen outer reaches, one from the blazing sun, were set on a collision course. The coincidence of timing was striking. Just days after SWAN's brightness outburst, the sun sent one of its most powerful pulses straight toward its path. Suddenly, the comet wasn't just a beautiful sky object, it was a test subject in a natural experiment between starfire and cosmic ice. For scientists, it meant one thing: every telescope, every satellite, every camera needed to be pointed at SWAN, ready to watch history unfold in real time. The solar storm of September 28th didn't head toward Earth. But the geometry of space had something unusual in store. Calculations showed that the coronal mass ejection, racing outward from the Sun, would pass through the same region of space occupied by Comet SWAN's ion tail. That's an extraordinary coincidence. Comets don't often line up with solar eruptions in such a precise way. Why does this matter? Because a comet's ion tail is made of charged particles, essentially plasma, the same substance that makes up a CME. When the two collide, the results can be spectacular. In past encounters, comets struck by CMEs have experienced dramatic transformations. Glowing streaks bending sharply, sudden kinks appearing like knots in a rope, or even entire sections of tail snapping off and drifting away like a torn flag in the wind. For SWAN, the timing couldn't have been more dramatic. Its tail was already unusually wide, more than 5 full moons across, and highly structured. A CME hitting it would act like a cosmic stress test, stripping, twisting, and possibly even tearing away parts of the delicate plasma stream. Observers around the world began to anticipate a rare celestial show. A comet visibly reshaped in real time by the raw power of the Sun. This wasn't just about beauty. Events like these are windows into how space weather truly works. By watching SWAN's tail react, scientists could measure the density, speed, and magnetism of the solar storm without relying only on spacecraft instruments. The comet itself became a detector, its shimmering tail recording the invisible forces sweeping through interplanetary space. For the public, it offered a front-row seat to a cosmic alignment that may not repeat for decades. On one side, an icy wanderer from the outer reaches of the solar system. On the other, a fiery outburst from our nearest star. Their paths overlapped not by design, but by chance, reminding us how, every so often, the universe arranges its own rare alignments for anyone willing to look up. As the coronal mass ejection barreled toward Comet SWAN, scientists focused on one critical question: the orientation of its magnetic field. A CME isn't just a cloud of charged particles, it carries its own magnetic structure, twisting and flowing through space like an invisible storm front. If that magnetic field happened to align southward relative to the Sun's, something extraordinary could occur: magnetic reconnection. In this process, the solar wind's field locks onto the magnetic environment of SWAN's ion tail. The effect is sudden and violent. The tail can disconnect completely, breaking away in a matter of minutes. Imagine watching a glowing plasma ribbon stretching millions of kilometers long suddenly snap, drift, and vanish into the void. Such tail disconnection events are rare. They've been seen before, most famously with comets Encke and Lovejoy, but almost always from limited angles or after the fact. With SWAN already dazzling observers worldwide, this time was different. Thousands of telescopes, from backyard cameras to space-based instruments, were primed to capture the event in detail like never before. For researchers, this was more than a spectacle. It was an opportunity to study magnetic reconnection on a solar system scale. Usually, this process is measured in Earth's magnetosphere or in the Sun's corona, environments difficult to observe directly. But a comet's tail offered a giant visible marker. If reconnection occurred, it would be written in light across the sky. For sky watchers, the anticipation was electric. Would the CME simply bend SWAN's tail into a new shape? Or would the entire plasma stream rip free, leaving the comet momentarily bare before growing a new tail in the days to follow? No one could say for sure, but everyone knew one thing. If the Sun's magnetic field tilted the wrong way, SWAN was about to undergo one of the most dramatic transformations a comet can experience. And we might all be lucky enough to witness it. All the drama of SWAN's outbursts and solar interactions is leading up to a spectacular moment. On October 21, 2025, Comet SWAN will make its closest approach to Earth, just 0.25 astronomical units away. That's about 39 million kilometers. In cosmic terms, that's practically in our neighborhood, making this one of the closest bright comets in years. But the timing adds something even more remarkable. This close pass happens under a new moon. With the moon completely absent from the night sky, conditions will be as dark as possible. No lunar glare, no washed-out tails, just a pristine canvas for SWAN to display its full brilliance. For skywatchers, it's a dream alignment. A bright comet sweeping by during one of the darkest nights of the entire year. Across the globe, astronomy groups are already preparing. Observing campaigns are being organized, star parties scheduled, and equipment checked and rechecked. Amateur photographers will be out in force, capturing SWAN's sprawling tail against constellations, while professional observatories will use the moment to gather data at an unprecedented scale. Even casual stargazers will be able to step outside, look up, and, without a telescope, see history written across the sky. The proximity also offers science a golden opportunity. At this distance, radar facilities may be able to ping the comet directly, measuring its nucleus and rotation. Spectrographs on Earth-based telescopes will resolve the chemistry of its coma in exquisite detail, helping scientists piece together not only SWAN's recent outbursts, but also its deeper story, where it came from, and what it's made of. For the public, though, the message is simple. Mark your calendar. October 21st, our Sammanfort will not just be another night. It will be the night when a wandering ice ball from the edge of the solar system comes closer than almost any of us will ever see again. Glowing bright against a perfectly dark sky. A cosmic encounter, written in starlight. As if Comet SWAN's flyby weren't enough, the universe has decided to add another twist to October 21st, 2025. On the very same date, another cosmic traveler takes center stage, 3I Atlas, the interstellar object that has been the focus of worldwide attention since its discovery. On this day, Atlas reaches superior conjunction, positioning itself on the far side of the Sun relative to Earth. At first glance, this might sound like poor timing. Superior conjunction makes Atlas difficult to observe directly. But in reality, it creates a once-in-a-lifetime scientific moment. The ability to compare, side by side, the behavior of a classic solar system comet and a confirmed interstellar visitor, two icy wanderers from entirely different origins under nearly identical solar conditions. For astronomers, this coincidence is a gift. Comet SWAN, born in the outer reaches of our own solar system, carries the chemical fingerprints of our cosmic backyard. 3I Atlas, on the other hand, is alien, formed around another star system, shaped by physics and chemistry beyond our Sun's influence. Watching both objects interact with solar radiation and solar wind within days of each other allows researchers to measure the similarities and differences in their activity. Will SWAN's response to the solar wind mirror what Atlas shows under conjunction? Will its chemistry, tails, or outbursts reveal clues that can distinguish homegrown comets from interstellar ones? The answers could redefine how scientists identify future visitors from beyond our solar system. For the public, October 21st becomes more than just a comet flyby. It turns into a cosmic double feature, a radiant comet blazing across dark skies, paired with the invisible but deeply significant alignment of an interstellar object. Two travelers, two stories, one stage. It's the kind of celestial coincidence that reminds us the universe doesn't follow our calendars. It writes its own, and sometimes it schedules something unforgettable. When Comet SWAN sweeps past Earth on October 21st, the view won't be reserved for professionals or those with access to massive observatories. This is a comet designed for everyone. Both hemispheres will get their share of the show, making it one of the most accessible sky events of the decade. For northern observers, SWAN will climb higher in the evening sky as October progresses, stretching its tail across familiar constellations. In the southern hemisphere, the comet will appear even earlier in the night, giving stargazers long windows of visibility. No matter where you are, the recipe for the best view will be the same: a dark sky, away from city lights, and a clear horizon. The tools needed are modest. A simple pair of binoculars will reveal SWAN's coma as a glowing ball and trace its sweeping tail in fine detail. Small backyard telescopes will bring out delicate structures within the dust and ion tails, fans, striations, and ripples sculpted by the solar wind. Even a basic DSLR or smartphone camera with a tripod and a few seconds of exposure can capture the comet's luminous streak against the stars. But the real magic is that no equipment is strictly necessary. If SWAN maintains its current brightness, many people will be able to step outside and spot it with the naked eye. A rare gift in an age where city lights often wash out the night sky. For photographers, the timing could not be better. The absence of moonlight during the flyby will allow SWAN's tails to shine against truly dark skies. Long exposures will record the comet stretching across wide fields of stars, producing images that will likely define astronomy galleries for years to come. Whether you're an amateur astronomer, a casual stargazer, or simply curious enough to step outside, Comet SWAN is setting the stage for a spectacle that connects us all. For a few nights in October, everyone with eyes to the sky will share in the same wonder, watching an ancient visitor light up our world. Comet. SWAN's close approach isn't just a spectacular sight. It's a rare chance for science to observe cosmic forces in real time. The combination of its proximity to Earth and the interaction with the recent solar eruption creates a natural laboratory that can't be replicated in any Earth-based facility. As the comet hurtles through space, scientists will be watching how its nucleus, coma, and tail respond to the solar wind. The ion tail, in particular, is a delicate structure of charged particles that reacts instantly to changes in solar plasma and magnetic fields. If the coronal mass ejection intersects the tail, researchers could witness kinks, disconnections, or rapid shifts unfolding in minutes rather than months, a unique window into magnetic reconnection and plasma physics. Ground-based telescopes, satellites, and the coordinated efforts of amateur astronomers all contribute data to this unprecedented experiment. Observers will measure brightness variations, capture spectral signatures, and track structural changes in the tail. Every observation builds a dynamic picture of the forces shaping not only comets, but also the broader heliospheric environment of our solar system. The opportunity extends beyond physics. By combining data from this flyby with observations of interstellar visitor 3I Atlas, scientists can compare the behavior of solar system-borne comets to objects from beyond our star system. This could provide insights into the chemical makeup, formation, and evolution of objects formed in completely different stellar neighborhoods. For the public and the scientific community alike, SWAN's flyby is a reminder of how dynamic and interconnected our solar system truly is. Every moment of observation, every image captured, becomes a piece of a story that unfolds in real time. A story of ice, dust, solar energy, and cosmic motion, offering a glimpse into processes that govern the universe on a grand scale. This is not just stargazing, it is science in motion, a chance to witness cosmic change as it happens, and to be part of a global effort to decode the secrets of a traveling comet.